Hi, I'd like to finish up a multiple imputation covering the case two method moment estimation. So the Bayesian imputation, we use Bayesian imputation for M independently. So the first step is the P step, posterior step. Second step is the I step, imputation step, right? So we use P step to generate eta star and then plug in to obtain the imputed value. And then once we obtain the imputed value, we plug into the method of moment estimator and then then obtain the imputed estimator, J's imputed estimator. So then we will average over J to obtain the multiple imputation estimator. So to understand the uncertainty and investigate the static properties, we can first decompose this way. So that is this is the imputed, right? This is the posterior value and then the difference. So that is imputation randomness. So there's a randomness I step, right? And this is the P step. And we here, if Y is completely observed, that means we don't have a missing data for I. Then there's nothing missing, right? So then there's no so then this is just equal to G because the expectation here. So definition of M is the conditional expectation, but there's nothing to condition on because I mean actually we condition on observation, full observation. So then there's a expectation. Uh, uh, there's nothing missing, right? So then the expectation disappears. Okay, and then now so let's investigate the first component. And so the first component, so J's imputed value, you can do the same Taylor expansion to obtain this way. So you linearize with respect to eta hat, then you have m dot, which is the partial derivative. So then you basically you have this guy, the first component has a two part. So that end of the day, you have a three component. So this is the, again, I step. This is the P step, right? The first one is the genuine that we plug into MLE. So we plug into MLE to obtain the method moment estimator using conditional expectation. So this is conditional expectation of the GY given data and at the head MLE, right? So that is, so we have a three. So this is kind of orthogonalization, right? The Pythagorean theorem. And so we can, we now, this is for J, and then we have average. So this is the over J equal to 1 to M of psi hat star J, something like that, right? So this is this one. So then we have three orthogonalization. So, and then three terms are independent. So we have this three term. And also remember the second term is actually equal to expectation over BM. Remember why? Because the lemma 5.1 is expectation BM is a sigma 1 minus a sigma 1 2, right? So I mean the let's write it this way. Variance of the of psi hat I star 1 minus covariance psi hat I star 1 psi hat I star 2. So if you look at the formula here, right, you have three terms, and then the variance minus covariance. The covariance, you have only the first component is only in common, the other two are independent. So that means you the expectation of M essentially is the variance of the second and third term, which is this one. So that is lemma point one. And first remark one, this is the so moment estimator. And if you look at the difference between the two, turns out that you can use the Taylor expansion, and then because these two are independent, because it's MLE, right? So this is MLE. So this is we have independent. So then the variance of this difference is so what is eta hat P, by the way? Eta hat P is more like a conditional expectation of the GY given Y observed and the eta hat, right? MLE. So this is more like a best predictor. Best predictor. So that's the kind of so the imputation and the best predictor has a variance. So the variance of this guy is this one, and the variance of this guy of this guy is this one. So it turns out that this is actually equal to the expectation of BM, which is by lemma 5.1, right? Yeah. So that's interesting because the remark one basically says your okay. The difference. So the best predictor is actually the equal to the limit, probability limit of the MI. So I had MI with M goes to infinity. So that is basically is what's going on here. So basically we are eta hat PMI variance is a variance of eta hat N plus variance of the eta hat MI minus psi N plus covariance, right? So basically, if this is estimated by expected of the WN, and this guy is equal to PM by lemma 5.1. So it's actually lemma 5.1. And this is 0. So if this, well, this is not 0. So this is actually bias. This is the bias of the variance of MI, which is this one. So is it correct? Something's not really correct. Sorry. Okay, that's correct, right? This is, well, this is just N, right? So this is actually minus, right? Minus bias, which is this one. Okay. So so that is basically the main message. So now let's see how this various bias term shows. And so this is a simple example. We have a regression model, and so generally theta, so it's same thing, and we have a MAR. I guess later. So So a type P is a best predictor, and which can be written as something like this. So that is M. This is actually G, right? Yeah. So conditional expectation, and so we can basically the covariance it has this form, and this is, and so after some algebra we can obtain this one, and this covariance term is in many cases positive because this is kind of low bound, Kramer-Rao or low bound type. Okay, I think that's all for a multiple imputation. Okay, thank you.